Yay! 4 of 4. Okay. And this is only, I think, 4 questions. Cool. So, problems. A study of king penguins looked for a relationship between how deep the penguins dive to seek food and how long they stay underwater. So, depth and how long they stay underwater in time. For all but the shallowest dives, there is a linear relationship that is different for different penguins. The study gives a scatter plot for one penguin titled The Relation of Dive Duration Y to Depth X. Duration Y is measured in minutes and depth X is measured in meters. The report then says the regression equation for this bird, so this specific bird, is y hat is equal to 2.69 plus 0.0138x. Okay, so what is the slope of the regression line? And then interpret this value in context. So again, the slope is always the value that's with the x. That's just how slope works. And let's go ahead and say what it is and interpret it in context. The slope is 0.0138. And it would probably be, well, let's just interpret it in the context the way we always interpret it. For each additional meter of depth, the duration of the dive for this penguin is predicted to increase by about 0.0138 seconds. Okay. So always make sure you're answering the full question. There we go. Next up, does the y-intercept of the regression line make sense in context? If so, interpret it. If not, explain why not. Okay. So the y-intercept of 2 point, oh, it's in minutes. Excuse me. Minutes of 2.69 minutes for a depth of 0 meters does not make sense in context because it wouldn't take over 2.5 minutes to not dive. Also, the problem states that this model does not apply to very shallow dives. Okay. So, whenever you're trying to figure out if the y-intercept makes sense in context, just say, okay, well, if x is 0, so they went 0 meters and it took over 2.5 minutes. No, that doesn't make sense. Sometimes it will. In this case, it doesn't. All right, see, according to the regression line, how long is a dive to a depth of 200 meters expected to last? So this is going to be our x value. And so we're going to say y hat is equal to 2.69 plus 0.0138 times 200. So the predicted value here, the predicted duration, 0.0138 times 200, is 5.45 minutes. And then okay, so we were given the expected value. Or excuse me, we were given the depth and then we calculated the expected value of 5.45 4 or 5 minutes, or the predicted value. If the actual dive took 6 minutes, what is the residual? So the actual was 6. I'm going to always write this actually. Actual minus predicted. Always what you actually got first. So it's true, like actual minus mean, actual minus predicted, actual minus expected. Whatever it is, actual is first. So the actual is 6. The predicted is 5.45, which means our residual is 0.55 minutes. And so I'm going to say 0.55 minutes. And then that means the prediction was an underestimate. The predicted time was less than the actual time. This wasn't asked for, but just to put that in context. Okay. 2. There is a linear relationship between the number of chirps made by the striped ground cricket and the air temperature. A least squares fit of some data collected by a biologist gives the model y hat equals 25.2 plus 3.3x, where x is the number of chirps per minute and y hat is the estimated temperature in degrees Fahrenheit. What is the predicted increase in temperature for an increase of 5 chirps per minute? Okay, so there's 2 ways to think about this. We can start with some actual numbers, right? What if we go from 0 to 5? This represents an increase in 5 chirps per minute. And so then we can calculate the 2 predicted temperatures and find the difference. So let's do that. So the y hat when x equals 0 is 25.2 plus 3.3 times 0, which is just 25.2. And the y hat when x is 5 chirps per minute is 41.7. So then we could do that minus 25.2. And we get 16.5. So that is degrees Fahrenheit. That's our predicted increase in temperature given an increase in chirps per minute of 5. Now, the other way you can think about this is because we're adding 25.2 no matter what, we're just going to be multiplying this by 5 additional times, right? We're going to get 5 additional 3.3s. So the way I would think about it is I would just do 3.3 times 5. And lo and behold, we also get 16.5 degrees Fahrenheit. Both are totally fine. If this makes more sense to your brain, it is not a waste of time to do it that way. If you see, oh, it's just we're increasing the x by 5, so we're going to get 5 additional ones of these, great. Also good. Cool. All right. Number 3. Long-term records from the Serengeti National Park in Tanzania show interesting ecological relationships. When wildebeest are more abundant, they graze the grass more heavily, so there are fewer fires and more trees grow. Lions feed more successfully when there are more trees, so the lion population increases. Researchers collected 19 years of data on one part of this cycle, wildebeest abundance in thousands of animals, and the percent of the grass area burned in the same year. The results of a least squares regression on the data are shown below. So this is just the relationship between the wildebeest abundance and the percent of the grass area burned. Give the equation of the least squares regression line and define any variables you use. Okay, so we've got our y hat equals, And here's our coefficients on the wildebeest in thousands and the constant. So our constant is 92.29. And then because this is a negative slope, I'm going to say minus 0.05762. They gave us a regression output, so let's use all their numbers. X. So this is always going to be our X variable. So X equals wildebeest abundance in thousands, and Y equals the percent of grass area burned. Okay, we write our equation, we defined our variables. B, explain what the slope of the regression line means in this setting. Notice, we're practicing interpreting the slope quite a lot. So, for each additional 1,000 wildebeest, the percent of the grass area burned is predicted to decrease by 0.05. Well, so those are the percent. So let's multiply that by 100. So by 5.762%. For each additional 1,000 wildebeest, the percent of the grass area burned is predicted to decrease by, I'm going to say about, right? Give that really clear signal that you know this is an estimation. You know this is a predicted value. Okay. Good. Find the correlation. Interpret this value in context. So the correlation, we haven't talked about this yet. The correlation is not R squared, but it's going to come from it's going to come from using R squared. So correlation is R. So if R squared, and we're always going to use the non-adjusted one, if R squared is 0.646, we're going to take the square root, and R is equal to 0.646 square rooted is 0.803. Now, this one gets a little feisty. Because it's a negative slope here, our R value is negative. When we take the square root, we're always going to get the principal square root. We're always going to get the positive version. But it's also true that if negative 0.803 were squared, we'd also get this exact same R squared value. So we have to use the fact that it's a negative slope to know that our R is negative. For interpreting that value, because this is pretty close to -1, right? The closer you are to 1 or -1, the stronger it is. We're going to say there is a reasonably strong negative relationship between wildebeest abundance and percent of grass area burned. We can't know from R whether it's linear or not. This is the strength of the linear relationship, so we can know the direction and the strength from R. All right. Interpret R squared in context. Okay, this is a sentence stem. Memorize it. Okay. We're just going to start with 64.6%. We're just using that R squared value of the variability in percent grass area burned can be explained by the variation in wildebeest abundance, right? It's just that percent of the variability in the output in the response variable can be explained by the variation in the explanatory variable. Explained, explanatory. Okay, find and interpret a 98% confidence interval for the slope of the regression line. Clearly, I didn't put a lot of space here. I'm not expecting you to do the full out confidence interval. We'll get to those, don't worry. But for here, for the slope of the regression line. So I'm just going to write my formula. This is in your formulas. Slope plus or minus t star times the standard error. The slope is negative 0.05762 plus or minus. We'll get t star in a second. The standard error is what goes right next to the slope, right? The standard error coefficient. So that's going to be times 0.01035. And then for 98%, we're going to do t star is equal to inverse t. The area is going to be 1 minus 0.98, because that's our 98% interval, divided by 2. The degrees of freedom. Researchers collected 19 years of data. So we're going to say 19 minus 2. When we do that, we get 19 minus 2. We get a t star of 2.567. And that's what goes here, 2.567. Oh, that's a fun number. All right, and so now we will pop that into our calculator and get our interval. So, negative point. Be careful how you type this. 0.5762. I'm going to do the minus first. 567 times 0.01035. So our interval goes from negative 0.0842 all the way to negative 0.0311. We'll round to the same decimal point. Some of you have asked if here and there, like, is it okay that both of these are negative? Yeah, it just means that we're looking at a negative slope, right? We want both those numbers to be either negative or positive, because then that means we have a significant value, right? We're going to have evidence that the slope is negative or that the slope is positive. If this value is negative and this value is positive, then there's a possibility the slope is 0, which means we have no evidence of a relationship. So that's the find. Now we got to do the interpret. We are 98% confident that the interval negative 0.0842 to negative 0.0311 contains the true value of the slope for the relationship twixt wildebeest abundance, say between wildebeest abundance maybe we need to type this. I think we need to type this. Ah, I don't know what just happened there. Oh, I see. Yeah, I really like this app, but it's not the absolute best for everything. Okay, let's try that again. Let's type it like a reasonable human being. Okay, we are 98% confident that the interval from negative 0.0842 to negative 0.0311 contains the true slope of the relationship between wildebeest abundance and percent of grass area burned for uh ah, trying to shrink it. Where are we? Uh for Serengeti National Park? Oh, will it not let me make it smaller? Come on, man. There we go. Now we're cooking with gas. For this area in the Serengeti National. Uh, was it a park or a monument? Park. It's important. There's a difference between national parks and national monuments. Not as big as difference between national parks and national forests, but there's difference, so you want to be correct. All right. Lovely. Below is the scatter plot and residual plot for the data collected in question 3. Is a linear model appropriate? Why or why not? Okay. So, based on the scatter plot, we could say a linear model appears to be appropriate because like the data appears to be roughly linear. This is pretty close to it is because it is, but in this case that's kind of what we got, right? It's a tautological argument, but we'll run with it. Okay, dokie. Here, based on the residuals, we could say the linear model seems appropriate because there does not appear to be a pattern in the residuals. Right? So when we're looking at the residuals, we don't want to see a pattern. When we're looking at the actual data, we do. All right. Good job. Thanks for bearing with me. I will see you on the flippity flop.